Have you ever stopped to think about this secret chemistry that's happening all around us, all the time? I'm talking about in the food you eat, the soap you use, even inside your own body. Today, we're going to pull back the curtain on the invisible but super powerful world of acids, bases, and salts. So, let's start with something we've probably all felt. You just finished a fantastic, huge meal, but now, oh boy, that telltale burn of indigestion is kicking in. That's your stomach making a little too much acid. So what's the move? Do you reach for something acidic, like lemon juice, or maybe something different, like baking soda mixed in water? By the time we're done here, you'll know exactly which one is the right call, and more importantly, why.
All right, here's our game plan. We'll start with the absolute basics. What's the deal with acids and bases? Then we'll put on our detective hats and learn how to spot them. After that, we'll see what happens when they actually react with each other. We'll uncover a secret ingredient that makes it all possible, learn how to measure their strength, and finally, we'll see why this stuff is so important to our world. Okay, first things first. Let's meet the main characters in our chemical story, acids and bases. And trust me, they have very distinct personalities.
So what are the dead giveaways? Well, acids, think of vinegar or lemons, they usually have a sour taste. Bases, on the other hand, like baking soda or soap, tend to be bitter and feel kind of slippery or soapy to the touch. But, and this is a big but, tasting random chemicals is a terrible idea. So scientists use a handy tool called litmus paper. The rule is simple. Acids turn blue litmus paper red, bases do the opposite, turning red litmus paper blue. It's like their chemical calling card. So if tasting is out of the question, how do we actually tell these things apart safely? Well, it's time to become chemical detectives and start looking for clues. Our number one tool for this job is something called an indicator. And the name says it all, it indicates if something is an acid or a base just by changing color. Litmus paper is a famous one, but you'd be surprised how many others there are. Some might even be in your kitchen right now. And here's where it gets real. You ever spill curry on a white shirt? I know I have. Well, that yellow spice turmeric is an amazing natural indicator. The second you start scrubbing that stain with soap, which is a base, you'll see it turn from yellow to a reddish brown. That's not the stain getting worse. That's chemistry in your laundry room. But what if you can't see a color change? Well, some indicators are even sneakier. They use our sense of smell. These are called olfactory indicators. Basically, their smell changes or even disappears completely, depending on if they're in an acid or a base. You know that really strong, distinct smell of onion or vanilla or clove oil? Well, if you add a base to them, that signature smell gets completely destroyed. It just vanishes. But if you add an acid, the smell sticks around. It's just another really clever way to solve the mystery of what you're dealing with, just by using your nose. Okay, so we've got the identification part down, but what happens when these things actually do something? Let's get into the action and check out their reactions. One of the most classic and honestly coolest acid reactions is what happens when they meet metals. If you drop a little piece of zinc into some acid, right away you'll see it start to fizz and bubble like crazy. That gas it's making is hydrogen. And the best part is how we can prove it. If you trap those bubbles and bring a tiny flame near them, you get this really satisfying pop sound. It's like a tiny little explosion that confirms, yep, that's hydrogen gas. But what about the ultimate showdown, acid versus base? When they go head to head, something called a neutralization reaction happens. They basically just cancel each other out. And what are you left with? A salt and good old water. This right here is exactly why you take baking soda, a base, to calm down that extra stomach acid. You're just neutralizing it. You know, acids are actually really predictable. When they react with something like chalk or limestone, which are metal carbonates, they always make a salt, water, and carbon dioxide gas. And when they react with metal oxides, which is basically rust, they also make a salt and water. They follow the same patterns over and over. All right, get ready for a pretty big reveal here. All of these properties and reactions we've been talking about, they only happen because of one secret and very common ingredient. Take a look at this. We have a simple circuit with a light bulb.
If you put the wires into a solution of acid, boom, the bulb lights up. But if you try the exact same thing with sugar water, nothing. So what gives? Both solutions have hydrogen in them. Why does the acid solution conduct electricity when the other doesn't?
The secret ingredient is water. You see, when you put an acid in water, it breaks apart and releases positively charged hydrogen ions. We call them H+. And when you put a base in water, it releases negatively charged hydroxide ions, or OH-. It's these tiny, free-floating charged particles, these ions, that are zipping around and carrying the electric current. That's what makes the bulb glow. And if you need the final smoke and gun proof, here it is. If you take pure, dry hydrogen chloride gas and touch it to a piece of dry litmus paper, absolutely nothing happens. It doesn't act like an acid at all. But the second you add water, that gas dissolves, releases its hydrogen ions, and that same piece of litmus paper instantly turns red. Without water, an acid can't show its true colors. So, we know what acids and bases are, but they're not all created equal. Some are incredibly strong, while others are pretty mild. So the question is, how do we measure that strength?
For that, we use something called the pH scale. You can think of it as a power meter for acids and bases that runs from 0 all the way up to 14. Right in the middle, at 7, is perfectly neutral. Anything below 7 is acidic, and anything above 7 is basic or alkaline. And here's the wild part. The scale isn't linear. A pH of 3 is 10 times more acidic than a pH of 4. So even a small change in the number means a huge difference in strength.
Let's put this into perspective. That lemon juice in your fridge, it's way down there with a pH of about 2, super acidic. The water from your tap is usually hovering right around a neutral 7. And then you have something like household bleach, which is a really powerful base, way up at a pH of about 13. This scale really helps us understand the chemical world we live in. So a number on a scale, why should you care? Well, it turns out that maintaining the right pH isn't just interesting science, it's quite literally a matter of life and death. For instance, when the pH of normal rainwater dips below 5.6, we officially call it acid rain. And that seemingly small shift is enough to change the pH of entire rivers and lakes, making it incredibly toxic for fish and all the other creatures that live there. And it's not just the environment, it's inside of you too. Your body works tirelessly to keep the pH of your blood in a super narrow range, between 7.0 and 7.8. If it goes outside that, you're in big trouble. Plants need the soil to be at just the right pH to grow, and your stomach needs to be extremely acidic to digest food. So you see, pH balance is everything. So let's wrap this up with a big, out-of-this-world question. We now know just how critical a balanced pH is for life here on Earth. So think about our planetary neighbor, Venus. Its atmosphere is choked with thick clouds made of sulfuric acid. Knowing what you now know about the intense power of acids, what do you think? Could life as we know it possibly survive in an environment like that? It's definitely something to chew on. Thanks for watching.
Like, share and subscribe.